Okay, this is Pancast for the fourth question of the final Physics 101 in spring 2018. We have two spaceships, both of which have mass m, which are tied to each other by a cable of length L. They are rotating around their common center of mass, so something like this. With period t, the ships are far away from any other masses and gravitational force they apply to each other can be neglected. That's great. Find the tension in the cable. Okay, so if I'm given the period t, then frequency will be 2 pi over t, right? Which is actually the angular velocity of this with respect to the center of mass. So what's the acceleration of one of these masses? This will be v squared over r, but r is L over 2. So it's going to be 2 over L times v squared. But v is omega times L over 2. So it's going to be L over 2 omega squared. That's the acceleration. And all of this acceleration must be given by T, tension in the rope, or let's call it F if you want. F is going to be ma. F is going to be m times L over 2. Omega squared is 2 pi over T squared. So our result is 2 pi squared over T squared and L. That's the tension in the rope. Good. A motor in one of the ships pulled the rope so that the distance between the ships is reduced to L over 2. Now, these guys are getting closer. I know that angular momentum is conserved, so what I expect them to do is they will start to rotate faster with some omega prime. Now, what was my initial moment of inertia? I have two ships, both of them have mass m, they are L over 2 away from the center of mass. What's my final moment of inertia? I have two ships, both of them have mass m, but they are L over 4 away from each other. Initial angular momentum is omega I times II. Final angular momentum is omega final times I final. Initial angular momentum is equal to final angular momentum. So let's write this as follows. 2 pi over initial t is I initial, 2 pi over t final. I final, 2 pi is cancelled. Apparently t final is I final divided by I initial times initial period. So I need I final divided by I initial. I final divided by I initial is 2m's cancelled, L squares cancelled. It's essentially 1 over 16 divided by 1 over 4. It's going to be 1 over 4. So T final will be 1 over 4 times the initial period. Which means, period is 1/4, which means that they are rotating with essentially 4 times the angular velocity. How much work has the motor done to pull in the rope? So to be able to shorten the rope, the motor must do some work. There was tension in the wire. So what was my initial energy? There is only kinetic energy. We are asked to ignore all gravitational influences. So what was the initial energy? The initial energy was 1/2 m times v was omega times L over 2 square. Or I can basically, well, twice that, right? I have two of those. Or I can This is m over 2, cancel. I have omega square L square over 4. So this is going to be 1/4 m omega square L square. Good. How about the final energy? I have two ships. Both of them have 1/2 m. Now I need not the initial omega, but the final omega. And omega final is 4 times omega initial, right? So this is going to be 4 times omega, but I'm actually at distance L over 4 square. So force cancel. This is going to give me m omega square L square. Apparently the final energy is 4 times the initial energy, which means the work done must be the difference between those 3/4 m L square over omega square. We are not given omega, we are given the period. So m L square for pi square t square, force cancel, 3 m L square pi square over t square is our answer.